Welcome to Tutorial 3. If you have not completed Tutorial 1 and 2, please do so now. In this tutorial, we'll be preparing our ethanol water mixture as feed for a distillation column we will solve in a future tutorial. We'll do this by adding a pump, a heater, and a pipe segment object. From the object palette, drag a pump, a material stream, and an energy stream onto the flow sheet. I usually decalculate my solver. Now we could select the pump, and in the selected object properties, we'll choose the inlet stream to be the mash, the outlet stream to be the material stream 5, and the energy stream to be energy stream 000. Change the calculation mode to outlet pressure and change the downstream pressure to 2. Leave the efficiency at 75. Now grab a heater from the object palette. This is a simple heater with only one material stream inlet and one material stream outlet. It is different from a heat exchanger. Click and drag an energy stream and a material stream onto the flow sheet. You can leave these with their default names. Select the heater, assign it inlet and outlet streams, as well as an energy stream. For the calculation mode, change to outlet vapor fraction. Leave it at 0. This will bring our stream to its bubble point. Now that we have a stream of ethanol and water near its bubble point, slightly above atmospheric pressure, we'll attempt to use an example of how one could calculate the pressure drop through various instruments such as ball valves, elbows, pipe lengths, and so forth. I'm going to rename this stream feed, as it will be feeding my column. You should first assign the inlet stream. In this case, it's material stream 6. Next, assign the outlet stream, which will be the feed, and the energy stream, which is energy stream 2. I usually like to invert these guys horizontally to show that they're energy exiting a process. Select the pipe segment, and near hydraulic profile, bring up the edit hydraulic profile window. I'll choose a straight pipe, quantity 1, 5 increments, that's calculation increments. The material is PVC. I use the length as 1,000 centimeters, an elevation of 100, external diameter of 30 millimeters, and an internal diameter of 28 millimeters. Now this is not a standard pipe, but I'm just using arbitrary values to show how flexible this program can be and how powerful of a calculation tool you have at your disposal. You leave elevation at 0. I'll use the same external diameter and internal diameter as the straight pipe. I'll also include a ball valve. As you can see from the drop-down list, there's many options to choose from. I'll say maybe I have, 6 ball valves in this pipe string. We'll change it to PVC. We'll have to assign a length here, an elevation, an outside, and an inside diameter. I'll go ahead and change my lengths to 10, but I'll leave my elevations at 0. Keep the same external and internal diameters and click apply. I'm also going to change my pressure drop correlation to the Lockhart method. And for thermal profile, I'll go down here and let DWSIM calculate as if there was a breeze with an ambient temperature of 25 degrees Celsius. Using insulated PVC pipe with polyurethane foam. So you can X out of that, and now we're ready to solve. Click the play button and then the recalculate all. And our simulation should solve. Hover around your pipe to make sure that your numbers are reasonable. And that concludes this tutorial.